Say to one and all. So let us proceed with the electronic configuration in NLX method. So here we have seen already that N means nothing but principal quantum number, L is nothing but subshell name, and X is nothing but number of electrons present in the subshell. Right. So we'll see some examples for this NLX method. Along with that, we have to see what are the different rules we follow for this. So before going to that, we should know in every shell how many subshells are there. In every subshell how many orbitals are present. So first of all, let us see about that. After that, we'll see how to write this electronic configuration in NLX method and even in electron orbital picture or electron orbital method. Right. So coming to the number of subshells present in a shell. So let us take first shell. In this first shell, n value becomes, n means nothing but principal quantum number. Principal quantum number becomes 1. So because of that, azimuthal quantum number values, only 0 is possible because azimuthal quantum number value starts from 0 onwards and the maximum value is n minus 1. Right. So that is why L values are only one value possible, that is 0. Right. So n value, that is nothing but shell number, principal quantum number, only 1 is there. Azimuthal quantum number value, only 1 is possible, that is 0. That means nothing but it is S subshell. Only one subshell is present. So coming to M value, what is this M here? It is nothing but magnetic quantum number. Magnetic quantum number value starts from minus L, proceeds up to plus L, the middle 0 also. Minus L, 0, plus L. Right. So based on that, if you see L value 0, so M value, only one value is possible there. Based on that, we can say how many number of orbitals are present in the subshell. Actually, magnetic quantum number gives us the information about orientation of the subshell. Orientation of the subshell in the presence of magnetic field. On which axis the subshell is present. Along which axis the subshell is present. Right. So only one orbital is present here. So in S subshell only one orbital is present. So that is why number of electrons present in that. S subshell is 2. One orbital, 2 electrons. One subshell, one orbital, 2 electrons. Coming to second shell. Second shell means nothing but n value is 2. Principal quantum number value is 2. So L values here we have 2, 0 and also 1. 0 means nothing but S subshell and 1 means nothing but P subshell. 0 is nothing but S subshell and 1 is nothing but P subshell. So in this S subshell we have only one magnetic quantum number, that is 0. So only one orbital is there. And in P subshell we have totally 3 values for this magnetic quantum number, minus 1, 0 and plus 1. Minus 1, 0 and plus 1. So because of that, what we can say here, 3 orbitals are present. What are the 3 orbitals present in P? Px, Py, Pz. Px, Py, Pz. The dumbbell shape of the P orbital, if it is lying along the x-axis, it is called as Px. If it lies along the y-axis, it is called as Py. And if it is lying along the z-axis, it is called as Pz. Right. Next, if you go for third shell, in second shell only 2 orbitals. 0 and 1 are the L values because 0 onwards up to n minus 1 values are present. Third shell, if you see 0, 1 and 2. These 3 values are possible for L. Right. So based on that we can say 0 means nothing but S, 3s orbital, 3s subshell, and this is 3p and this is nothing but 3d. So in S orbital, S subshell we have only one orbital. In P subshell we have 3 orbitals, Px, Py and Pz. And D orbital we have totally how many orbitals present? Minus 2, minus 1, 0, plus 1 and also plus 2. How many values are there total together here? 5. 2L plus 1 is the number of the orbitals present in one subshell. Number of magnetic quantum number values number of magnetic quantum number values for one L value. So the same formula we can write number of orbitals present in a subshell. So here how many are there? 5 are there. So these 5 will say as that 5 orbitals are present in 1 d subshell. What are those? Here we have, as we have here d orbitals. What is the shape of that? Double dumbbell shape. Double dumbbell. 2 dumbbell shapes are there here. So those are dxy, dyz, dzx. 3 orbitals. Along with that we have here dx square minus y square and also dz square. These are the 5 orbitals. dxy, dyz, dzx. dx square minus y square and dz square. These are the 5 orbitals present in one d subshell. So like that, if you see number of electrons in first shell only 2 because only 1 orbital is present. Second shell we have total together 4 orbitals. 4 orbitals, so that is why number of electrons present in second shell is 8. Third shell, if you see here we have SPD. Altogether here we have 9 orbitals. 1 plus 3, 4, 4 plus 5, 9. 9 orbitals are there. That is why maximum number of electrons accommodated in third shell is how many? 2 into 9. That is nothing but 18 electrons. Right. Like that, if you take fourth shell, how many values of these L values are possible? N value is 4. L values 0, 1, 2, 3. So 0 means only one value is there for M, and 1 is nothing but minus 1, 0 plus 1, and 2 minus 2, 0 minus 1, 0 plus 1 and plus 2, and 3 minus 3 minus 2 minus 1, 0 plus 1 plus 2 and plus 3. How many altogether here? 7 values are there for this F subshell. So here altogether we have 7 orbitals in F subshell. So altogether how many orbitals are present in this fourth shell? 1 plus 3, 4, 4 plus 5, 9, 9 plus 7. Altogether here 16 orbitals are present in fourth shell. That is why number of electrons present in fourth shell is nothing but 32 electrons, because in each orbital 2 electrons are accommodated. Like that, altogether 16 into 2. 16 orbitals into 2 electrons. Right. So 32 electrons, maximum 32 electrons are accommodated in fourth shell. So let us see some of the rules and regulations in this NLX method, how we have to write. So here mainly we follow 3 rules. So the 3 rules we'll see here. First rule we have here, that is off-bow principle. Off-bow principle. So before going to this off-bow principle, we should know what is this. Off-bow means, it is not a scientist name. Off-bow means nothing but building up. Building up in the sense, according to the energy level. According to the energy level, we will arrange the subshells. According to the energy level, we will arrange the subshells. Right? Then we'll allow the electrons to enter into them. We write what is that systematic arrangement of the electrons is nothing but electron configuration. No. So that systematic arrangement, how we are arranging the subshells, that is depending on the amount of energy present in the subshell. So here we say in first shell we have only one subshell, that is S. Second shell we have S and also P. Right. Third shell we have S, P and also D. Fourth shell we have 4S, 4P, 4D, 4F. 4 subshells are there. Fifth shell we have 5S, 5P, 5D, 5F, even 5G also possible, but till now any element is not discovered which is containing that, so we are not writing here. Sixth shell if you see 6S, 6P and also 6D I am writing here. In future we may get after that 6F, means element which is containing 6F also. Till today we have only up to 5F. Next, 7th shell will have 7S and 7P. 8th shell will have 8S. Like that it will continue. But any element is not discovered till now, till today, which is containing 8 shells. Up to 7th shell, it's completed. Means electrons are present in 7th shell in one element. Up to there only it has been discovered. So 8th shell we are not writing here. Now just to put a circle around this. After that we'll see what is this rule actually. So this diagram, whatever we are going to draw, it is drawn by the scientist known as Euler. So this diagram is called as Euler diagram or Euler's chart, Euler diagram. So here how we are arranging these subshells. These subshells are arranged according to their energy. But we don't know what is the energy present in the subshell. So how to find out how much energy is there for the electron present in that particular subshell? Just we'll add the n value and L value. What is that n value and L value? Here if you take 1s, in this principal quantum number n is 1 and subshell is s, means L value is 0. So we'll get the total value as 1. If you take 2s, 2 plus 0, we'll get 2. We'll take 2p here. Now this line, whatever the order we have written here, the same manner we are going to take. 2p means 2 plus 1, that is nothing but 3. Then we'll take 3s here, 3 plus 0, 3. 3p we take here, 3 plus 1, we are going to get 4. Then 3d, 3 plus 2, 5. Next, after 3d is completed, we'll come to 4s. For 4s, 4 plus 0, that is 4. 4p, 4 plus 1, that is 5. 4d, 4 plus 2, that is nothing but 6. 4f, 4 plus 3, that is nothing but 7. 5s, we take here 5 plus 0, that is nothing but 5. 5p, 5 plus 1, that is 6. Like this will continue. Right. So now we'll arrange these subshells according to their energy level. First of all, we are going to take the n plus L value. Wherever it is minimum, there the electron will enter. N plus L value is minimum, electron will enter into that particular subshell. After it is filled, then it will enter into the next n plus L value. Right. So here we have the least value 1. So electron will enter into 1s. So I am writing here arrow mark. This arrow mark will show us into that particular subshell the electron is entering. So in 1s, 2 electrons will be accommodated maximum. After that it is filled, then it will enter into second shell, 2s, because 2 value is there for this. So into second shell it will enter. After that, where it has to enter, because here 3 values there here for both 2p and also 3s. 2p we have here 3 and 3s also 3. So here first of all we have seen wherever n plus L value is less, electron will enter into that particular subshell. If these two values are equal, then what happens? Electron will enter into the subshell wherever n value is less. If n plus L values are similar for both the subshells, 2p and also 3s. For these two we got same value. So that is why what we'll do here, wherever n value is less, that subshell will take into consideration. So 2p. After 2p is completed, then 3s. Because here for both of these, 3 value is there, n plus L value. Next, after 3s is completed, these 2 completed. After that, here we have 3p and also 4s. For both of that, 4 values. But already we have seen wherever n value is less, if n plus L values are similar, n value is less, into that particular subshell, electron will enter. So that is why we will enter into 3p, after that 4s. You can see mostly wherever we are writing this arrow mark, no, on that arrow mark, what are the subshells are present, for all those n plus L value will be equal. Right. Next, 3d, because here 3d 5, after that 4p, after that 5s. For all these 5 values there, but less n value, after that more n value, then after that still more n value. After that here, after 5s is completed, 4d, 5p, 6s. After 6s is completed, 4f, 5d, 6p, 7s. After 7s completed, 5f, 6d, 7p, then after that 7p, 8s. Like that, electrons are accommodated in these particular subshells. So this is a diagram or chart which is known as Euler's chart. Based on that only we are going to arrange the electrons in that particular subshell. So this is a Aufbau principle based on n plus L value. Based on n plus L value, we are going to arrange that subshells. Into that subshells, electrons will be accommodated. So the diagram is known as Euler's diagram. Right. Then second rule we'll see here. In this second rule we are going to write, when we write electron orbital method. Electron orbital method. So what is that method known as? What is that rule known as? It is nothing but Hund's rule. Hund's rule. So here this Hund's is nothing but the scientist's name. Hund has given the rule for us, Hund's rule. So in this Hund's rule, what we are going to write here, if you are writing electron orbital method, this rule we are going to follow, as I already said. So in this rule, what we will do is, in one particular subshell, many number of orbitals are there. All that orbitals should be filled with one electron each. After that only pairing should start. Here if you say S subshell, we have only one orbital. So we are going to show that orbital with the help of a square. So if it is the first electron, second electron will write anyway like this only. But P subshell, if you see, in this P subshell we have total together 3 orbitals. These 3 orbitals you can write in the form of one word known as degenerate orbitals. Degenerate orbitals, nothing but whoever the orbitals are having same amount of energy, those can be called as degenerate orbitals. In these degenerate orbitals, first of all, orbitals, every orbital should be filled with one electron each. After that only pairing should start. So first, second, third, fourth electron will enter here, fifth electron, sixth electron. Like that we have to continue. But not here. If you want to write fourth electron, second electron, if you want to write like this only here, it's not correct. This method is not correct. If you want to write second electron, what we have to do here? In these 3 orbitals, first, second. But not first and second like this. This is wrong method, this is correct, and this also is correct. Right? So this is Hund's rule. Next, one more rule we have here. This is known as Pauli's exclusion principle. Pauli's exclusion principle. So here this is an exclusion principle which is given by the scientist known as Pauli. So according to this principle, any 2 electrons of an element will not have all 4 quantum numbers similar. Any 2 electrons of an element will not have all 4 quantum numbers similar. At least one difference will be there. Right? So to understand that only, we'll take small example here. The element which contains just 2 electrons will take. So here we have helium which contains only 2 electrons. So for this helium, we write the electron configuration 1s2. Right? 1s2. In this 1s2 we have 2 electrons. What are those 2 electrons? We will show with the help of the electron orbital method. Right? So first electron, second electron. So for this first electron, we will write all n value, L value, M value, S value. What are these n value, L value, M value and S value? Principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. For second electron also we will write all the 4 values. So for this n value, it is present in first shell. So we will write principal quantum number value 1, azimuthal quantum number value. As it is there in S subshell, we will write 0, M value also 0. As it is rotating in clockwise manner, how will identify that? Up arrow is written, that is nothing but clockwise manner. Electron is rotating around itself in the clockwise manner. So we write here plus half. Then coming to this side, 1 because it is present in first shell, S subshell, S orbital, then minus half. So at least one difference we are getting here. If you don't want to use this one, if you don't want to follow the rule, then what we have to write? Both up arrows only will write. Then what it becomes? All the 4 quantum numbers will become similar. So that we should not do. Right? So this principle, Pauli's exclusion principle will say us that any 2 electrons of an element will not have all the 4 quantum numbers similar. Right? So based on this only, we'll see some examples for the NLX method and also electron orbital method. Now here we have some elements. Instead of writing in line, just here and there like that we'll write. So here we have an element, atomic number 5. I'm not saying the name of the element. You know already it is nothing but boron. I want to write the electronic configuration. So when it is 5, we'll write here 1s2, 2s2, 2p1. 5 we are writing like this. First shell, only s subshell, 2 electrons. Second shell, 2s, 2 electrons completed. Then electron will enter into the next. Half-bow principle we have to use here. Now I am taking here atomic number 11. 1s2, 2s2, 2p6, 3s1. Right. I am taking here again atomic number 22. 1s2, 2s2, 2p6, 3s2, 3p6. After that 4s, not 3d. Because here both of them are having the value n plus l value 4. 3p6. Next 4s. How many electrons are there? Here total together 22. 2 plus 2, 4 plus 6, 10. 10 plus 2, 10 plus 2, 12 plus 6, 18. 18 plus 2, 20. 20 plus, after 4s is completed, 3d. 3d, 2. 10, 10, 2. 22. Right. Here we have some exceptional cases, like if you take atomic number 24, it's nothing but chromium. For this chromium, we have small exceptional case. We'll write here 1s2, 2s2, 2p6, 3s2, 3p6, 4s, and 3d if you want to write. Actually, we'll be writing like this, 4s2, 3d4. But here what happens in d subshell, if you see, 5 orbitals are there. In these 5 orbitals, if 5 electrons are there, if it becomes half filled, it will get stability. So that is what happens here. Instead of 4s2 and 3d4, it becomes 4s1 and 3d5. One electron will jump from 4s to 3d. Same like that for atomic number 29, copper also will write like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. By filling, by getting the fully filled orbitals, that element will get the stability. Further only it will write. So one electron from 4s will jump into 3d. By that it will get stability. So these are some of the rules and regulations which we follow to write the electronic configuration in NLX method. Like that, if you want to write in electron orbital method, what we have to write? Mostly we will be writing this method to show the chemical bonding, to show the hybridization and all. We will be using that. So here, last shell electrons only we will be writing here, not the innermost electrons. So first means in 2s, this electron, third electron in this element, fourth electron, fifth electron. Like that, here also one electron is present in third shell. So that by seeing this, we can easily identify how many number of valence electrons are there. If you want to write for 3D, now for example, here we have 3D5. In this 3D5, what we have to do? Just write all the 5 squares together to show that 5 orbitals are present in D subshell, and write here 5 electrons. We are writing this method, we are writing in this manner to follow this rule known as Hund's rule. Right? So like this, we'll write here. Any 2 electrons if you take, they will not have all 4 quantum numbers similar. That is according to Pauli's exclusion principle, and we have arranged these electrons according to their energy level. Right? So if you like the video, please share, comment and subscribe my channel. Thank you.